So it's a really good partnership that we have. And part of that partnership is you, my students. So I'm really happy. We've managed to do some things this semester with COVID. It's hard to do laboratory research when you really are restricted in time and space and getting together. But let's finish up the semester. You guys sent me some research ideas, and one thing that I realized when Kyle brought it up that he wanted to look at the HSPs for an oil is that most of the substances that are typical in a lab, and even in sort of non-lab situations like oils, they're already in the HSP database. And I thought, oh, I never really showed you guys. I sent you an Excel file that had the HSP database, but let's look at the Hspip software. So I sent you a link for downloading that, but I'm going to share my screen and I'm going to run that. But first, let's learn about smiles. So did y'all look at the smiles code stuff?
I looked at it a little bit.
Yeah, so this is, again, this was just a report that was put up on the CPA website that is pretty easy to find. You can also find it in Wikipedia and so on. But this is a really handy little thing. So you can just, that is really simplified right there. That's ethane, right? If you want to make decane, you just put 10 C's on a line and that's decane. It doesn't get any easier than that. So the reason you need to learn smiles is because the Hansen Solubility Software has incorporated smiles code into its software. And if you can write the smiles code for a compound, then you just paste that into the Hspip modeling tab, and it will tell you the HSPs for that substance and a whole lot of other things. So anyway, this is some pretty cool stuff. And you can write out ethene other ways. You could put the hydrogens in there if you wanted to. Here's how you do like ketones. Notice how you're putting this parenthesis equals oxygen between the carbons, and so that's that carbonyl bonded to that second carbon. If the carbon doesn't have 4 bonds, then it fills in everything with hydrogens. And so you're looking at this is a carbon bonded to a carbon. So that first one only has 1 bond to a carbon. And so it's got, by default, 3 bonds to hydrogens. Then this next one has 1 bond to the carbon on the left, 1 bond to the carbon on the right, and then in parentheses, it shows it has 2 bonds to an oxygen. So it's a ketone, a carbonyl, and it's done. There are no hydrogens on that carbon. And then, and if you wanted to do an aldehyde, then you just end with that. And so that carbon has a single bond to the carbon on the left, a double bond to the oxygen. It has 1 valence left over, so they stick a hydrogen on it. So that's how you do aldehydes. Branched alkanes. So here we have, let's see, 2-methylbutane. Okay, so this little guy right here is the methyl. You see how that's working? So you got 2 carbons, and then you have it branch off to 2 carbons, and then you have 1 carbon left over. You can write this many different ways, I'm sure. You could have probably put just 1 carbon in parentheses, and that would have put a methyl on there. And so there's some redundancy built into the language, which is not great if it's redundant, because they were wanting to use this for searching. Like if you could use this code, and if somebody could populate a database of all the known chemistry substances with the smiles code, because it's a single line, then you could have a really fast way to search for compounds on the internet that was structure-based instead of CAS number-based, right? I can come up with the smiles code in my own head, but I can't come up with the CAS number in my head.
Right.
So it would really be nice for searching, and that's what they were trying to do in the early 80s, late 80s, is to come up with a way to type in chemistry into the search engine. And I don't know, maybe they got it done. Let's come up here and let's type in 2-propanone. So let's see if we get something. C equals OC. Okay. Okay, so Hspip. Huh.
Looks like PubChem too.
Yeah,
Maybe.
it didn't come up with that specific one, but it definitely looks like you can search Smiles code on Hspip. Let's change that. Let's go.
Man, that's complicated.
CC. All right, let's see. See, it wants to add all that other stuff. Hey, what do you know? So that's pretty sweet. So they, their goal was for that to happen. Okay. And so if you can write out the Smiles code, then you can search structures if you don't know the name. And sometimes, like I was 2-propanone, but what if you didn't know that the common name was acetone?
Mm-hmm.
And you say, well, I know the common names. Do you really? Tell me what is it? See, I can't remember this one. It's always one that gets me. It's a common name for 5 carbons, but I can't remember what it is. Because we would say pentane or pentene or something like that, but it's a common name for that, and I always forget it. And when I see it, I was like, oh yeah, I remember not knowing that, and now I know it. Yeah, but when I don't see it, I don't know it.
Yeah,
so
I don't know it either.
Yeah, it's a. Let's just do it. Let's do search. So 1, 2, 3, 4, 5, and I'm going to put an OH on the end, so make an alcohol out of it. There's a common name though. Amyl.
Amyl. I've heard. Yeah, I've heard.
How many of you knew what amyl alcohol was? Right. So that's the one that so I knew that it was 5 carbons, but I couldn't remember the common name for it, and so I used the Smiles code, and I knew that I would get it, and I got it. Amyl alcohol. So perfect example of trying to deconvolute the names of compounds using the Smile code. Okay, so that was, I couldn't have engineered that better. So that's Smiles code, and that's great. Now these are small compounds. The Smiles code gets much more involved when you start to have ring structures. Like here's cyclohexane or hexene, you've got a double bond there. And so you use labels like you're labeling the carbons and you're saying this carbon is attached to that carbon, or they might be the same carbon. Let's see how this works.
I think they're different.
Yeah, they're different carbons. They're just bonded to each other. So they're saying this carbon is bonded to carbon 1. They're bonded to each other. Okay, here's naphthalene. Let's see if that works in Hspip, okay?
Yeah.
Hope this doesn't bore you.
I'm assuming the 2 is for double bond.
No, I think it's just different bridge carbons.
Oh, yeah, no, you're right. Yeah.
Waiting, it says. Boom.
Oh, hey.
That's pretty cool, huh?
Yeah.
Who knew that was naphthalene? I mean, baby, look at that. C1, C, C2, C, 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 C2, C, C1. And you got naphthalene. Yeah. So that's pretty slick. And you could work your way around it. Like you could start at the end of the molecule, C1, then you go up to a carbon, and then you have C2, which is going to be a bridge carbon. And then you go C, 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 C2, because that's the bridge carbon, C, C1, which is bridge to the 1. And so you can work your way around naphthalene.
Does it matter where you start?
I don't think so. Yeah,
Okay.
I don't think so. Yeah. That's where the ambiguity comes. Yeah. Yeah. Anyway, so that's pretty sweet. And then you have, I don't know about the +1. What's that? Carboxymethyl pyridinium N +1. I guess it's trying to show that it's a
charged.
Yeah, it's the 4 coordinate N. The what do you call that? Yeah, like the ammonium.
The ammonium salt thing. Yeah.
Yeah.
+1 charge. Yeah.
Yeah. Okay, so that's Smiles code. Is everybody kind of cool with that? Not that you know how to do it, but you know how to find it and search it and look it up. Okay. Any questions on that before we move on?
No, sir.
Okay, cool. All right, so then Hansen Solubility Parameters. This is where I got the software. Okay, this is the official site for HSP and HSPIP. There's Charles Hansen himself. Great guy.
He mentioned you in his
got
book.
off on it. Oh, he did?
Yeah, he talked about you.
Oh, yeah, that's right. There's
glass.
a deal about the glass. Yeah, about glass. Yeah, and they saw that, and that's how I got connected with them. They said, "Can we put this example in our book?" And I said, "Yeah, sure." So, the way I found out about the Hansen Solubility Parameters was 2010. I had a government contract with Pantex, and we were looking at the solubility of explosives in various solvents, and they were sending me data. Basically temperature solubility curves, okay? And then I was doing the thermodynamic modeling to find delta G of mixing and so on for the solvents. And I had a student do a literature search, which a lot of students, I think, sometimes feel it's just busy work, right? Oh, he doesn't know what to tell us to do, so he told us to go look at the literature. It's not busy work. I mean, one, it gets you familiar with the literature, and two, it helps the professor to put you guys out there as feelers to find out what's going on, in the literature, and then you come back and it's an efficient way to scour the literature. So a student came back a week later and she said, it's Katie Roethlisberger, and she's got her PhD now from A&M in agricultural engineering or agricultural chemistry, I'm not sure. But she got her chemistry degree at SAM, bright girl. And she said, why are you not using the Hansen Solubility Parameters for this report or for this research? And I said, what are those? Right? So nice. She discovered them for me. I mean, I would not have known anything about them if she hadn't discovered them. And so then she brought me some papers that she found, and that was the beginning of it, 2010. So I mean, it was totally student discovered. And for my area, it was a student discovery of this model for solubility that was in the literature since the 60s that I had never been taught, never come across. So it's been great ever since. I've made great use of them. So obviously there's this package, this Hansen Solubility Parameters in practice I bought several years ago. So let me run HSPIP software here. I just loaded it. I thought I had it on this machine, but I didn't. So this Hiroshi Yamamoto, he's a Japanese computer programmer, and he's the one that wrote this, a lot of the software. Stephen Abbott wrote a lot of it too. Charles Hansen didn't write much software, but he was the scientist behind most of it. And they change these little tabs up here, and they keep adding functionality. And this is interesting. I haven't seen the Smiles tab before, so let's look at that. Oh, what?
Oh,
you can copy Smiles from your computer. Interesting. So anyway, I clicked that Smiles tab, and it said, "See via structure drawing in your local browser." So I said yes, and now we have a structure drawing. This is cool. Functional group. What do y'all want? I want a nitro. That's cool. And I want an amine.
There's one down there. Oh, wait, no. Yeah. No,
That's the cyno.
no, up.
Well, maybe for an amine, you just put a nitro in there. No, it's undo. We have an
Undo.
undo. Okay. Okay, let's try that. Oh, no, undo.
Could,
What if I drag it out?
yeah.
Nope.
Or go to the top and add a bond,
Yeah,
and then change that carbon to.
yeah. Yay, okay, so ortho nitroaniline. All right. So, fantastic. Now what do I do?
What? Scroll down on the page. What is it? Below. Oh.
Oh, just instructions.
Shows molecule smiles. Okay, so the smile.
Oh.
You click the smiley face to get the smiles code.
Wow.
Oh, that's cool. Okay.
That's cool. Okay, you have access to this now.
That's cool.
Okay.
Yeah.
Yeah. So we select that cute little puppy there. Hit Control C for copy, and then go back over to HSPIP. And then there's this do-it-yourself DIY. I think it's kind of funny. You get this form here, and there's a bunch of different ways to calculate the Hansen solubility parameters, and there's other kinds of things in here. But this YMB is their one they recommend. It's Yamamoto, the guy that wrote it, and then MB is called molecular breaking. And so he breaks the molecule up and does functional groups analysis and comes up with HSPs. So he has a certain amount of dispersion, polarity, and hydrogen bond associated with the aromatic ring, and then a certain amount associated with the nitro and a certain amount associated with the amine. And so that's what he's doing. He's adding those contributions together and coming up with the HSPs for the whole molecule. So that is pretty slick right there.
Yeah.
And so then you come over here and you hit there used to be a little calculator button. Yeah, here it is, calculator. Okay. Chug, chug, chug. All right, it tells us the groups that it used. It has a primary amine group, a phenyl group, an NH2 on an aromatic group, and a couple of oxygens. So that's the group categories that the software used. And it gives us the D, P, and H values right there. Now they've added this new thing, donor acceptor, to kind of take into account whether this group can accept a hydrogen bond or donate a hydrogen bond. And so it's got a 4.9 donating character and a 9 recepting character, because it's got those 2 nitro groups, those big oxygens out there. It can receive hydrogen bonding. But like, think about acetone. Acetone has only the carbonyl. It can receive a hydrogen bond, so it's an acceptor, but it's not a donator. It doesn't really have any protic character to it, any kind of donation character to it. So this is these are the HSPs at 25C. You can change the temperature and recalculate, so they have temperature dependence in here. And then all of these other things are group additivity values. So you kind of take them with a grain of salt, but it's kind of a good guess at those values. We have the melting point, the boiling point, the refractive index, the density, molar volume, molecular weight. This stuff I don't know what ovality is, MCI. But over here we have the vapor pressure values, the Antoine A, B, and C coefficients, which will tell you the vapor pressure as a function of temperature, relative evaporation rate, flash point, viscosity at 25 degrees C, the oil water octanol partition coefficient. And I don't know what AOHR is. And then it's got this 3D structure, which is, it's not the best. Yeah. But anyway, isn't that incredible?
Yeah, that's pretty neat.
Yeah. So And so I think you can copy the full data to a clipboard, etc. So I would say explore this. You know, have fun with it. There's some things we can do with polymers too. Here's some solubility for all your polymers. And so if you wanted to know if, say, here's PVC, like if PVC was compatible with acetone or something like that, then you would want to look at the Hansen solubility parameters for PVC and look at the Hansen solubility parameters for acetone. And if they're too close together, then you know it's probably not a good idea to run acetone through PVC tubing, right? And so that's where the polymers come into play. It doesn't have an interaction sphere on here. I thought that would be nice if it did. Let's close this. Let's make a polymer, okay? So we come back up here to the smiles thing. And what kind of polymer do you want to make?
Polystyrene.
Oh yeah, the good old polystyrene. Yeah.
All right, let's go polystyrene. You good
The one
one, good
Dr.
one.
Hobbs always uses as an
Yeah.
example.
So the one that we know by heart.
All right, very good, very good. So we got their bond here. And then this is going to be the polymeration bond. So I think you just do this,
Yeah.
okay? And you do that, and you put an X. Let's see. That's the next
I
one, right?
think, yeah. I think add
So-
one more.
I
and
think
put
this is the
in
X
there.
and that's the X, right?
I think there's a second carbon before the X. That's what I think.
So
'Cause
this
you have
is
that double
X
bond.
here. I don't know how to do this. Speaking of X there. And so you're saying an X here or another one with an X?
Another carbon and then an X.
Really?
Assuming the X's are like
The connection
Yeah.
point, right? Where?
yeah.
Okay, so where's my eraser?
Uh,
Right here, probably.
yeah.
Oops. Okay. Not a problem. And you're saying another one like this and put an X there?
Yeah,
Okay.
I think.
Okay, so we'll see if that works. Then we do the smiles
Yeah,
code.
we'll see if it works.
It's ugly smiles code. And then we'll go over here. DIY. Polymers, where are you? Okay. Let's do 3 repeats just to see if it does it right.
Yeah. Does the model building thing give you a name? I know sometimes they can.
Yeah, like
generate a name.
if we did it right, then this would show right here polystyrene, because I guarantee polystyrene's in here.
Yeah, I would think.
Let's try to come up with something we want to do with it. Okay. There's you can create using this polymers thing. You come up with HSPs for particular polymers. So you would learn how to use the polymers tab. The YMB tab is just non-polymers, like just the whole molecule, right? Coming up with HSPs for that. There's also azeotrope stuff where you can put in 2 compounds and try to see if there's an azeotrope between those 2 solvents. That's pretty cool. There's solubility, which I haven't explored. Okay, so you can see what the solubility of a particular substance is in a particular solvent. Miscibility of 2 solvents, both temperature dependent and concentration dependent. So it would tell you what the upper critical solution temperature was and those kinds of things. I haven't done anything with surfactants, but here they are, So this is getting into the cationic and anionic stuff. So, that's something that the HSPs, I know nothing about in terms of using the HSPs in aqueous solution. And the reactions, I have no idea. So, but then you get into the Solvent Optimizer, and this is where if you have like if you have the Sharpie HSPs here for one of the spheres, right? You put those in here, Tanner, and then you can search for the best solvent, the best 2-component blend, the best 3-component blend. So once again, you put the target in here, so that would be the center of your sphere, and then you come up here and maybe click 2, and let's see. Yeah, so it's got benzoate and dimethylacetamide at a 6139 mixture. Yeah. So that's pretty sweet.
Yeah.
I guess I would like for you guys to let me know sort of what you're interested in researching with this software. This will be our final thing. And so let's make this just like a mini report, like a 2-page report. Okay. So tell me what you're going to research with this software. It could be anything, the polymers, it could be the solvent blend, azeotropes, or something like that. Do that over the next couple of weeks and just turn in a little 2-page report on how to use this software to do what you were set out to do, okay? So that I can learn some things from you guys about how to do the things that you were interested in. So this is real research. This is open-ended. This is whatever you want to look at. It might help, Tanner, if you've sent out the HSPs for like the artificial soil and the Sharpie marker. We have 2 spheres for the Sharpie marker so that people would have some targets if they wanted to do something like the solvent blend analysis.
Okay, yeah.
Yeah, so send that out to the whole group, or send it to me and I'll bounce it out to the whole group. If y'all are in a polymers class and there's some kind of crazy polymers that you studied, like maybe some of Hobbs's research polymers where we don't have the HSPs, maybe you could put those ring opening polymers in there. Yeah, who knows?
Yeah.
Is this too open-ended? Sometimes it's too open-ended and people just don't know what to do.
I was thinking that I could look at the surfactant thing and see.
Yeah.
I think that would be interesting to look into. See what you could show what surfactant was best for what soil and whatnot.
Oh, very good. Very good. Yeah.
Yeah, and see if we could kind of show that using ultrasonics with that.
Yeah. I like what you're saying there. So that's good.
I think the polymer thing sounded pretty cool.
Okay.
I might look into that.
Yeah, and so here's 2 reasons why you want to look at polymers and HSPs, okay? One is so that you can find something that will not attack the polymer, right? So materials compatibility. So whenever you're changing, like you have a gasket made out of Viton, which is a commercially available polymer. If you have a solution that's flowing through that system and it basically would dissolve Viton, that gasket's going to leak. That solvent's going to go in and eat a hole through that Viton and flow out. So that's materials compatibility is one reason why you want to look at polymers, and that is so that you can avoid attacking the polymer. And then sometimes you do want to attack the polymer. So sometimes you want to be outside the sphere and sometimes you want to be inside the sphere. So, it just depends if you're trying to remove the polymer or get the polymer and the adhesive off the surface. Then you want to interact with the adhesive and not the polymer. And so there's just different times when you either want to attack the polymer or not attack it. So yeah, I would encourage you to sort of look into the polymers tab and get familiar with some of the HSPs. Again, we've got HSPs for the solvents, and we have an HSP for the polymer, and you want those to be as far apart if you want them to be compatible, and as close together if you want them not to be compatible. like you want them, when I say compatible for polymer, I mean a solvent that will not attack the polymer.
Mm.
Right.
Okay. And when I say incompatible, I mean they're very close to each other. They dissolve and they interact. And so that's typically when we make things out of polymers, we don't want them to fall apart. Like a styrofoam cup, great for water, Coca-Cola, you know, my cherry limeades, but not good for acetone. Right? So if I'm trying to carry acetone around the lab, I don't want to use a styrofoam cup.
Something the HSP book mentioned was about how polymers, if you look at the HSP of the polymer compared to the monomers, like something about how like you could imagine the sphere being a lot closer to the center, like the radius of the sphere, I guess, being a lot smaller for the polymer than it would be for the monomer.
Yeah, that's a good thing to know. So you really just want to focus on the center of that polymer. And so, yeah, that sphere shrinks because, did they talk about the kinetic effect? I mean, it's hard to get a polymer to dissolve in solution because there's such long matrix of spaghetti, right? But you can get a polymer to swell pretty easily. So that solvent gets in there and it causes the polymer to swell. And again, that's an incompatibility thing. It reminds me of a story. I got a call from this guy who was installing solar panels in the California desert. And he had a materials compatibility problem. And he said, I need to know what to do because I have these plastic junction boxes that hold all the circuitry from the solar panels. And I make these by the thousands and I'm selling them to the solar panel people and they're fine. And they can handle the heat, all that kind of stuff. They're good. But whenever they glue them to the bottom of the solar panel, in just a couple of days, my plastic junction boxes just fall off. They fall apart. They crack open. They bust. And I said, well, you have what's called stress cracking. So they're gluing this plastic piece with a glue to a substance, and the solvent in that glue is swelling the plastic on those junction boxes. And so the back side of this package is swelling and the front side's not. And so it's called stress cracking. Like it just pops that plastic and it's broken. And so he needs to go in the lab right away and try a whole bunch of different store-bought glues and find which one doesn't cause the stress cracking and tell them to use a compatible glue. And that's all understandable through the Hansen Solubility Parameters. So if he knew that the solvent was a certain thing like hexane or heptane for that glue, and he knew that would crack his junction boxes, then he needs to tell them if you use that glue, then the warranty's void. Good. And just keep me posted if you have questions. All right.